Hello student, to the Foundation of Classical Electrodynamics course. Under module 4, today we have lecture 65 where we will continue our discussion on Maxwell's equation. So today we have class number 64 and our discussion on Maxwell's equation will going to continue. So Maxwell's equation. Let me write down the 4 equations that we discussed. The first equation is the divergence of E, that is rho by epsilon naught, that was the Gauss's law. Second equation was divergence of the magnetic field B, that is 0, telling that the magnetic monopole does not exist. Third equation was curl of E is equal to minus of del B del T, Faraday's law. And fourth equation was curl of B, that is mu 0 j, and that is Ampere's law, and we find that there is a serious problem in equation 4. What was that? So, if I take the curl from equation 4, what we get? If I take the curl both the side, if I take the divergence both the side, then I should have mu 0 divergence of j. Now, the left hand side is always 0, this is unconditionally 0, so it is always 0. But this is 0, this is not always 0. And it is 0 only for the steady current, condition of the steady current, that is when del rho del T is 0, because these two, I should write it here, that the two source term rho and j are associated with this very important continuity equation. So, they are not independent, rather they are related with this equation. So, the divergence of j 0 is eventually means del rho del T is 0. Now, obviously some modification are required. So, the Maxwells make this modification. So, today we will going to discuss this. So, Maxwell's modification. And the modification is this: the original equation was curl of B is mu 0 j, but Maxwell's added a new term that he says I am adding a term called mu 0 z d, but this is the Maxwell's contribution, where j d is E 0 del E del T. How this term appears, I will like to discuss this today's class, and it is called the displacement current. This is called the displacement current. So now let us have this term and check that everything is now work properly or not. This equation 4 is now identically left hand side and right hand side is valid or not. Then we will going to discuss about this ZD term. So we have now, after adding this, we are now having curl cross B is, now we have mu 0 J plus JD, that is the modification we are having, and JD is this. So I can write that the curl of B is mu 0 J with the addition of mu 0 epsilon 0 del E del T. So if I go back to the Faraday's equation, you can see that we had a similar looking equation here, where the curl of E is associated with the time rate of change of magnetic field. Here we have a similar looking thing. The curl of B is now somewhere depends on the time derivative of the electric field T. So this is the new term that we are having right now. Now let us go back to the case that whether the divergence of both the side of the equation is satisfying or not. So this is the modified equation, this is the modified fourth equation, modified version of the fourth equation. So that is the modified version of the fourth equation with Maxwell's correction term, and the Maxwell's correction term is this. This is Maxwell's correction term. Now let us check. Now we have divergence of curl of B in the left hand side, and that should be identically 0 without any condition. I mean unconditioned, this is 0. What about the right hand side? The right hand side we should have divergence of first term, we have mu 0 J, and then the modification, Maxwell's modification del E and del T. So that we are having. So left hand side is identically 0, right hand side we are going to check what is going on. Now this quantity I can have like mu 0, then divergence of J, mu 0 I can take common, and then we have plus epsilon 0, and del T I can switch the operator, divergence operator I can put inside the derivative because they are independent to each other, and then I am having this one. Okay. Now what is divergence of E from equation 1? Which we already wrote here, the very first equation, the divergence of E is rho by epsilon 0. So if I write that part, what is divergence of E? that is rho divided by epsilon 0. This rho has to be a function of space as well as time. So, I should now have, if I put there in this equation, so I can have that divergence of curl of B, which is 0. On the right hand side we have mu 0, then divergence of J plus epsilon naught, and then I have del T of this quantity. So, I eventually have del T of rho by epsilon naught this. So, now epsilon naught will going to cancel out, and eventually the thing we are getting is very interesting, and I should write it here like divergence of curl of B is equal to mu 0. Then I write here the equation in different color, that thus J plus del rho del T. Now, these things is a continuity equation. This is continuity equation, and we know that this equation is always 0. So, the left hand side is always 0. Now, after this modification done by Maxwell, very important modification, this is the modification we are looking for. So, after adding this term, what happened, that the left hand side and right hand side now both become identically 0, unconditionally 0, because continuity equation, I should write equation saying that plus del rho del T is equal to 0. That is the continuity equation, and it is there. So, that means a change of electric field induces a magnetic field. That is the outcome, physical outcome we are having. So, finally, we are having the equation that curl of B is mu 0 vector J plus mu 0 epsilon 0 del E vector del T, and that basically this term is saying that a changing electric field induces a magnetic field. Now, let us try to understand physically the concept of this displacement current that we put here. We put here, and as a ad hoc like addition, and then we find that after putting this addition, we have nicely matched left hand and right hand side when we take a divergence both the side. So, the left hand side is unconditionally 0 and right hand side also leads to a equation which is unconditionally 0. So, now we are going to understand the concept of displacement current. the concept of displacement current. Now, one can understand, this is a very standard way to understand this displacement current, and that is the capacitor problem. So, let us consider a model where a capacitor is charged. So, charging capacitor problem. What we have in charging capacitor problem? Suppose I have a, say I have a capacitor, two capacitor plate like this. So, this is one capacitor we are having, this is the capacitor plate, circular capacitor plate, say. So, they are now in charging condition. So, let us define few things. Let us define this radius to be r, and let us say the current that is flowing through this capacitor is I. This is the amount of current that is flowing. So, what happened that when the current is there, so this capacitor will going to be charged up. Now, the point is, if I try to find out the B at point P, so here at this point, suppose I want to find out the magnetic field, and we know that when we have a current carrying wire, it should produce some magnetic field around it, and if this length is say r, then the what should be the magnetic field that is produced here in this region. So, if I calculate, so suppose this is a point P. So, this is my point P. So, I should find out that B at point P, magnetic field B at point P is how much? I can use the Maxwell's the Ampere's rule, that the closed line integral B dot dl is equal to mu 0 and the current enclosed, that is my rule. So, here the amount of current enclosed is I and the dl is 2 pi r. So, I simply have B multiplied by 2 pi r is equal to mu 0, the current that is flowing through the wire, and I have B is equal to mu 0 I divided by 2 pi r. That should be the value of the magnetic field here in at point P. Now, if I want to find out the magnetic field in between this region, so I want to find out now the magnetic field in between this region here, say at distance r, and let us define a point here Q, then what should be the value, of this, okay, let me, this is not a continuous, so I should make a dotted line here, and from here it is r. So, what should be the field? So, B at point, so let us first try to calculate one by one. So, I want to calculate here B at, the question is what is the magnetic field at Q, point Q, what is this value, where R is say greater than equal to R outside the, so this is R, so this R, small r, is greater than the radius of this circular plate. So, if I calculate, I should get B dot dl, and that should be equal to mu 0 I enclose. And now you can see that there is no current that is enclosing. So, in principle the current is here and then it will go to charged up the capacitor. So, there should not be any current. So, that means in principle it should be 0. So, if it is 0, then obviously there should not be any magnetic field present here. That is a little bit weird, because here we are having the magnetic field and this side also I suppose to get the magnetic field because the current will be there, but in between the capacitor suddenly the magnetic field drops, suddenly the magnetic field is 0. So, obviously this is not feasible, there is a, obviously there should be some issue related to that, and that we are going to resolve here because we mention a displacement current. So, that means when there is a when the current is there, it will gradually, the plate is gradually charged up, and before going to a saturation state gradually it will going to charge up. So, the electric field in between these region is a time varying, there is a time varying change of the electric field, and as a result what happened that I should get the displacement current, and this displacement current should be one should take account. So, let us take account both the current now. So, it should be mu 0 and consider this I current is also there, which it should be I plus the displacement current. So, displacement current density, because I am taking the current, so I should write current density dot ds, that should be my displacement current, and this quantity is mu 0 I, if I is there, say in general I am just writing, then mu 0 epsilon 0, I should integrate it and it should be del E del T dot ds, because that is the way I define the displacement current, right. Now, so electric field E is here. So, I should know what is the electric field because we are dealing with the capacitor. So, the electric field E here is, which should be a function of time, should be the surface charge density, which is gradually increasing. So, I should write this sigma as a function of t divided by epsilon 0. That quantity sigma is again the total charge, which is also changing with respect to time, divided by epsilon 0 and the area of this material, area of this capacitor. So, A here is area of the capacitor. Okay. So, B at point, so what should be the value of the B? So, B, that is simply if I want to find out B, then I should use this expression. So, I should have the closed line integral B dot dl, and then I should have mu 0, and I am saying the current is 0. So, I should have 0 because I current is not there, right. This is my general expression. So, I current is not there. So, rest of the term if I write, it should be plus mu 0 epsilon 0, then 1 by epsilon 0 a, and then we have integration of d of q, which is a function of time, divided by dt and then ds. So, this portion is 0. So, epsilon going to cancel out. So, we have mu 0 divided by a, and this quantity dq dt is my current that is already flowing, right. I, which is simply dq dt, this is the current that is flowing through the circuit. So, I should have simply I here and then integration ds. This integration ds is over this capacitor area, which is also known. So, eventually, so I should write this I as IC to distinguish with the, this is the current that is flowing through the wire. So, IC should be this, and ds is A. So, integration, note integration ds is A. So, I should write it. So, it is simply mu 0 A and then I c multiplied by A again. A will going to cancel out, and eventually we have mu 0 I c, exactly the same value that we had, I mean that was supposed to have. So, now the left hand side, again left hand side is integration of b dot dl, and I want to find out at r. So, it is b multiplied by 2 pi r, which is mu 0 I or I c, and that value. So, that means b from here is simply, so I should write mu 0 a little bit lower because I did not put the denominator here. So, it is simply mu 0 I c. So, b is now mu 0 I c or I divided by 2 pi r. That is the value, that is eventually the same value that we are having. So, so this is the value when r is greater or equal to r. So, that means whatever the magnetic field I am getting here, the same magnetic field one should get by considering the the displacement current concept. Now, another question is there, what should be the find b when r is less than r, that means in between the capacitor. The capacitor. So, if I draw quickly what we had, so we had two capacitor like this, and suppose this is the, so current is flowing like this. So, I want to find out. So, what we want is we want to find out a region here. if I make a circle. So, note that this is R and it is smaller. So, smaller is less than R. Okay. Again, if I should calculate like this, so integration of B dot dl is equal to mu 0 IC plus ID. In general, ID is the displacement current, IC is the conduction, that is the current that is conducting. ID is epsilon 0 and then del displacement current is del. So, this displacement current, so J is mu 0. So, I should now ID in, I should write in terms of flux. So, it should be the electric flux divided by T, where phi E, because I had J D equal to epsilon 0 d E dt. E is a electric field, and in terms of, if I want to find out in terms of flux, then it should be the current, total current is J multiplied by the, so ID here is JD multiplied by the area ds, and if I integrate it over, so this area, if I multiply it with the electric field, so it multiplied by the area, electric field multiplied by the area should be the corresponding flux. So, that's why I can write it in the form of flux. So, it is electric flux, or so here I should write it E 0 and then del T, and I should have E here flux in terms of electric field multiplied by the area, and this area should be pi r square. Okay. That should be pi r square, and then I should have E. Okay, let me find out E then. E here is, which is a function of time, is sigma T divided by epsilon naught. So, that quantity I should write in terms of Q is Q as a function of T divided by E 0 and the area, and this area has to be the total area. So, I should have pi r square. So, here it is epsilon naught d dt of that thing I should write as pi r square, and here we should have epsilon 0 multiplied by pi b r square, and then I have dq, which is a function of t and dt. So, this eventually gives me IC multiplied by r square divided by r square. Okay. So, from here, so left hand side I still have B dot dl. So, if I want to execute the value of B, it should be B. So, integration of B dot dl can be written as B into 2 pi r, and that is IC, and then it should be mu into this quantity. Okay, I should have a mu here because B dot dl is mu 0, and this quantity ID I am calculating so far. So, ID multiplied by mu is there and IC is 0 in between. So, it is 2 pi r IC and then mu 0 r square divided by r. So, I should have uh, I should have B is simply IC, and then mu 0 r divided by 2 pi r square. So, this is the way the B will going to change, B as a function of r if I plot. So, you can see that in this point B is 0, and gradually if it goes, then this value is gradually increasing, linearly increasing, and exactly at this point it should be exactly at this point, at the edge of this, it should be mu 0 mu 0 IC divided by 2 pi r, and when it reaches the higher value, then accordingly it will going to change. So, anyway, the point is we have a understanding now that when the capacitor is charging, so let me summarize. So, we had two capacitor here, like this. So, this is the two plates are there in the capacitor, and they are charging by a current I. So, when they are charging, there is a change of the electric field. So, we had electric field in between this region, and this electric field is a time varying electric field, and this time varying electric field give rise to something called the displacement current density JD, which is simply epsilon 0 and the rate of change of time of the time varying electric field, and this basically give rise to the magnetic field with this formula. The magnetic field not only now give rise to produced by the normal current, but also there is a contribution of the displacement current that is producing the magnetic field, and the displacement current is associated with the rate of change of the electric field, that one can understand how it is produced in between these region in between two capacitor when it is charging. So, this is the way one can understand the displacement current. So, today I do not have much time, so I would like to conclude my class here. So, in the next class I will discuss more about the Maxwell's equation in detail and try to understand a few these constants, not constants, rather I should discuss about the gauge, the constraint, and how to put this constraint, and then understand that how one can write the electric and magnetic field, how the information from the Maxwell's equation can be extracted in the form of vector and scalar potential. So, with that note I would like to conclude. Thank you very much for attention, and see you in the next class.